Hello children, welcome back. Now let us start with the worksheet number 2 of gravitation. So let us move with the first question. So here we go with the first question. A body is weighed at the poles and then at the equator. The weight is. Children, if you consider the actual shape of the earth, it is little bulge at the equator and little lesser radius at the poles. The shape of the earth will be like somewhat oval shape, like egg shape, something like this. The shape of the earth is something like this, children. Okay. If you consider this as the equator, radius of the equator, and here the radius of poles, these two are North Pole and South Pole, and these are the equator. So the radius of the equator is equals to radius at poles. This radius, if you add 21 kilometers, this will give you the radius at the equator. So somewhat a slight difference in the radius is observed when compared to the poles and equator. So they both are not same. So a body is weighed at the poles and then at the equator. So as we know the formula for G as G is equals to Gm by R square. The value of G is equals to Gm by R square. Same body, so same mass, same gravity. So clearly we have G proportional to R square. If you consider the weight of the body at poles, because G is inversely proportional to R, as radius increases, this implies that as radius increases, larger the radius, lesser will be the gravitational. Larger the radius, lesser will be the acceleration due to gravity. So this implies larger the radius, so multiplying with m, lesser will be its weight. So wherever you have larger radius, there you will be getting lesser weight. And wherever you are getting lesser radius, you will be getting larger weight. So are the two radius equal or different? Different. So as we know that radius at poles is lesser when compared to the radius at equator, we can conclude that weight at poles is greater as compared to the weight at equator because inversely proportional. So where do you have body is weighed at the poles and then the weight at the equator will be greater than the poles? Weight at equator greater than the poles? No. Weight at poles will be greater than at the equator? Weight at poles will be greater than equator? Yes. At the poles, weight at poles will be equal to the weight? No, not equal. So at poles it is greater. Depends on the object. So the correct option is weight at poles is greater than at the equator because weight is equals to mg. Okay, larger the radius, lesser will be gravity. So larger the radius, lesser will be weight. Okay, at equator we have larger radius, so lesser weight. At poles we have lesser radius, you'll have larger weight. So moving with the next question, consider a satellite going round the earth. So we are given a satellite which going round the earth in circular orbit. Which of the following statements is wrong? What is a satellite going? This is your earth. Around the earth a satellite is there which is orbiting satellite. Consider a satellite going round the earth in circular orbit. Which of the following statements is wrong? It is a freely falling body. It is moving with constant speed. Why does it feel? Satellites will be continuously moving in those particular orbits. They won't fall onto the surface of the earth. So wrong statement. It is moving with constant speed? No. So as we know that it will be something like elliptical in shape. Okay. When it is elliptical in shape, larger the distance, faster it will move. Lesser the distance, slower it will move. So the speed will not remain constant. It is acted upon by a force directed away from the center and of the earth which counterbalances the gravitational pull. Of course it is true. So towards the center of the earth, the gravitational pull will be acting, force due to gravity, and to counter it balance that some additional force will be acting to balance that. So acted upon by some additional force, and this centrifugal force, let us say, is balancing the gravitational pull of the earth. So clearly Fg will be equal and opposite to that additional force that is acting. So it is acted upon by a force directed away from the center of the earth, which counterbalances the gravitational pull. Of course, statement C is correct. Its angular momentum remains constant. No, children, as we have just discussed that the speed is not constant, angular velocity is also does not remains constant. Okay, so now moving to the third question. A missile is launched with a velocity less than the escape velocity. So a missile is being launched with less than the escape velocity. If it is greater than or equal to the escape velocity, it will move away from the gravitational pull. Okay, and if it is launched with orbital velocity, it will be circulating around that planet. The sum of its kinetic and potential energy. Here you are asked to find out the energies. Okay, so with a velocity less than the escape velocity, what they have given? Less than the escape velocity. If it is greater than the escape velocity, it has a maximum amount of kinetic energy so that it can escape from the gravitational pull of the planet. But as it is launched with a lesser value than the escape velocity, it has a tendency, it has a lesser energy, okay, 0 or lesser than that value, so that it will come back to that surface. As a result, so coming back, you will be taking it as lesser value, taking it as negative, going away, you will take it as positive value. So here we have to consider the total energy as negative. Well, fourth question, maximum weight of the body is. Children, as we look at the earth, as we move away from the surface of the earth, the value of acceleration due to gravity decreases. Similarly, as we move towards the center of the earth also, the value of acceleration due to gravity decreases. Then where will be the maximum value of acceleration due to gravity? The maximum value of acceleration due to gravity will be on the surface of the earth. On the surface of the earth, it will be having the maximum value. Whether you go away from the surface of the earth, the acceleration due to gravity decreases, or else if you go towards the surface of the earth also, acceleration due to gravity decreases. So, where is the maximum value? Maximum will be on the surface of the earth. So, third option is true. Let us move to the fifth question, children. A geostationary satellite moves faster than the near-Earth satellite, has a time period less than the near satellite, revolves about the polar axis, or is stationary. The name itself indicates that geostationary. Geo means geo is related to earth. Stationary means at rest condition. You observe that whatever the satellites, okay, moon or any other satellite, if you consider that, whenever earth rotates about itself in 24 hours, okay, earth takes 24 hours to revolve around itself. Similarly, the satellite also takes 24 hours to revolve around the earth. So, if you observe those satellites from the surface of the earth, they both move with a constant speed. So, when they both move with the same speed, we observe as if it is at rest condition. So, geostationary satellites indicates that it is at stationary, it is in rest condition, it is in stationary condition. So, it is stationary in space. Well, moving to the sixth question, the acceleration due to gravity has the same value everywhere, has the same value everywhere on the earth, varies with the latitude on the earth, is greater on the moon due to its smaller. As we know that on moon it is lesser than the value of the earth, it is g/6, 1/6 of this. Latitude of the earth, yes, as we move away from the surface of the earth, the acceleration due to gravity decreases. So, this is a correct statement. Has the same value everywhere on the earth? No, we know that as we go away from the earth or we go into the surface of the earth, the value of g varies. So, even this is also same. Has the same value everywhere in the space? No. Different places, different acceleration due to gravity is observed. The only correct option is option C. Let us look at the next question, children. Seventh one. At what height is the value of G half that on the surface of the earth? So this model we already solved in the previous exercises. So even though, let us look at that carefully. What height is the value of G? Half that on the surface of the earth. Children, what is the formula for G? G is given as Gm by R square, where G, acceleration due to gravity on the surface of the earth, capital G, universal gravitational constant, M, mass of the earth, R is the radius of the earth. So it asks you to find out at some height the value of G. So new value of G, let me consider at GH, acceleration due to gravity, value of G, half that on the surface. This is what you have to find out. GH is equals to, G remains constant, mass also remains constant. So what changes? Distance changes. Earlier it was only R. Now from the surface of the earth, radius of the earth, it was taken to some place, say H. So now the total distance is R plus H. So R is now replaced with R plus H whole square. Same process, let us divide equation 1 and equation 2. Dividing 2 with 1, how much are you getting? GH upon G is taken as second equation upon first equation, Gm by R plus H whole square whole by Gm by R square. So solving this, Gm gets cancelled. Then you are left with reciprocal. You have R square by R plus H whole square. So clearly the value of GH by G is found to be R by R plus H whole square. So this is your value. And you are asked to find out the value of GH. So in order to find out the value of GH, bringing this G to the other side, G times of R by R plus H whole square. That's it. This is the formula. What is the value? Acceleration due to gravity at certain height H is acceleration due to gravity on the surface of the earth upon R times of R plus H whole square. So what is given, children? Given that at what height you are asked to find the value of H? G, half that on the surface of the earth. Given the value of GH is what? For earth, if it has G, at GH it will be G by 2. This is given condition. Nothing more, where R is radius of the earth, that's it. So substituting this, we have instead of GH, we can replace with G by 2 equals to G times of R by R plus H whole square. So you're asked to find out the value of H. This G and G gets cancelled. So 1 by 2 is equals to R upon R plus H whole square. This is square and this is 1 by 2. Taking square root on both sides, square root. So that square root of 1 by 2, you'll be getting it as 1 by root 2. Square root of R by R plus H whole square is R upon R plus H. Okay. So well, so 1 by root 2 is found to be R upon R plus H. Let us take the reciprocal of this, children. Taking reciprocal of this, 1 by root 2 will become root 2 and R by R plus H will become R plus H by R. The value of root 2 is taken as 1.414 equals to R is a common denominator for both. So R upon R will be getting it as 1 and this is H by R. So taking 1 to the other side, you will become 1.414 minus 1 will be equals to H by R. 1.414 minus 1 is equals to 0.414 equals to H by R, or the value of H is equals to 0.414 R. What is the value of H? 0.414 R. So for option 7th question, the correct option is 0.414 R. So that is the correct option. Everything is clear? So this is the formula, known simplified formula that substitute and simplify. So moving to the next question, children, question number 8. The value of the acceleration due to gravity at a height of 12,800 kilometers from the surface of the earth is. So directly you can take the formula as we have derived it earlier. GH is equals to G times of R by R plus H whole square. This is what we have derived in the previous formula. So as simplifying this, we get this value GH by G as R by R plus H whole square. Further simplification gives G at height H is G times of R by R plus H whole square. Even here also they gave the same formula. Instead of GH, they consider it as G dash, which is equals to G times of R by R plus H whole square. So whatever we derived the formula, the same they have given. So let us substitute this formula. The value of the acceleration due to gravity at a height h. How much is the height given? 12,800 kilometers. The height h itself is given as 12,800 kilometers. From the surface of the earth, radius, r is the radius of the earth and it was given as 6,400 kilometers. You are asked to find out GH. So substituting those values, we have G times of r, take it as 6,400 kilometers, r again 6,400 kilometers, h is given as 12,800 kilometers whole square. Or the value of GH is found to be G times of 6,400 upon this 0, 0, 8 plus 4, 12, 8, 9, 1, 9, 2, 0, 0 whole square. So proper simplification gives this 0 and 0 gets cancelled. 64 threes. Check for children, 64 threes, how much is that? 192. So 64 goes 3 times. Therefore, the value of GH is equals to G times of 1 by 3 whole square. Or GH is found to be G times of 1 by 9. But do you remember the value of G? The value of G is nothing but acceleration due to gravity. Its value is taken as 9.8. Hence, acceleration due to gravity at that height is 9.8 times of 1 by 9. This proper simplification will give you 9.8 by 9. How much it will be? 1.0 and 9 8s 72. So something like 1.088 so on you'll be getting. So the value of G is taken as 1.0888 so on meter per second square. Approximately if you round out this, you'll get it as 1.09 meter per second square. And the correct option is option B. Clear? Simple formula and simple application.